Tonight I want to speak with you about something that has haunted the greatest minds in physics for over 3 centuries, a mystery so deceptively simple that a child could ask it, and yet so deep that it reaches into the very foundations of how nature chooses to behave. The question is this: why does light always take the fastest path? Not a fast path, not one of many fast paths. The fastest, always, without fail, without exception, as if light somehow knows where it is going before it gets there. I want you to sit with that for a moment. Light leaves a source, a candle, a star, it does not matter, and it travels through space, or through glass, or through water, and when it arrives at its destination, we find without exception that it has chosen the route that took the least time. Not the shortest distance, the least time. These are not always the same thing. And that distinction, my friends, is where the story truly begins. Now let me first tell you who noticed this, long before I was born, long before quantum mechanics existed, long before anyone dreamed of wave-particle duality. The year was 1662. A French lawyer, yes, a lawyer, by the name of Pierre de Fermat, made an observation so radical, so philosophically disturbing, that it was not truly understood for nearly 300 years. Fermat stated what we now call the principle of least time. He said that light, in traveling between 2 points, always takes the path for which the travel time is minimized. This was not a guess. Fermat derived it mathematically. He showed that if you accept this principle, you can explain everything that was already known about light at the time. The law of reflection, which says that the angle at which light hits a mirror equals the angle at which it bounces off, and Snell's law of refraction, which tells us how light bends when it moves from one medium to another, from air into water, for example. Fermat showed that both of these laws are simply consequences of light always choosing the fastest path. Let us think about Snell's law for a moment, because it is the more surprising of the two. You have seen this effect yourself. Place a straw in a glass of water and look at it from the side. The straw appears bent at the surface. That is refraction. Light slows down when it enters water. It moves at roughly 3/4 of its speed in air. And because it slows down, it bends its path. But why does it bend in exactly the way it does? Fermat's answer is elegant. Imagine you are a lifeguard on a beach and a swimmer is in distress some distance out to sea, but not directly in front of you. You can run on the sand, but you can only swim more slowly through the water. What is the optimal path? You do not run in a straight line to the swimmer, because that would put too much distance in the slow medium, the water. But you do not run all the way along the beach until you are directly opposite the swimmer either, because then you've wasted time running. The optimal path is somewhere in between. You run at an angle on the fast medium, then enter the water and swim at a different angle through the slow medium. And the exact angles are determined by minimizing the total time of travel. Light does the same thing, automatically, instantaneously, every single time. Now here is where the philosophical trouble begins, because to minimize time, light must in some sense evaluate all possible paths and select the one with the minimum. How does it do this? Light is not a thinking thing. It does not have a brain. It cannot perform calculus before deciding which way to go, and yet it behaves as if it does. This is what troubled physicists for centuries, and this is where my work, my contribution, enters the story. But I'm getting ahead of myself. Let me first tell you about another man who wrestled with this question in a completely different way. His name was Christian Huygens, a Dutch physicist of the 17th century, and he had a beautiful idea. He said, light is a wave, and if light is a wave, then we can understand how it propagates by thinking about each point on a wavefront as the source of a new, smaller wave. These little wavelets spread out in all directions, and when you add them all together, they reconstruct the next wavefront further along. This is Huygens' principle, and it is one of the most powerful ideas in all of classical physics. Using Huygens' principle, you can derive the law of reflection and Snell's law of refraction entirely from wave mechanics. No minimization required, no mysterious path selection, just waves doing what waves do. So we had 2 pictures. Fermat's picture, light minimizes time. Huygens' picture, light is a wave that propagates by superposition of wavelets. Both of them work. Both explain the same phenomena, but they seem to be saying completely different things about the nature of light. One treats light as if it were an intelligent traveler. The other treats it as a physical wave with no choices to make at all. For 200 years, these two pictures sat somewhat uneasily alongside each other. And then came the 19th century, and James Clerk Maxwell and his extraordinary equations unifying electricity and magnetism, which showed definitively that light is an electromagnetic wave. Huygens seemed vindicated. Light is a wave. Fermat's principle of least time was perhaps just a mathematical curiosity, a useful tool, but not a fundamental truth about nature. And then came 1905. Albert Einstein, in one of the most audacious papers ever written, showed that light also comes in discrete packets, quanta of energy, which we now call photons, the photoelectric effect, light knocking electrons out of metal in a way that only made sense if light carried energy in concentrated bundles, not spread out continuously like a wave. Suddenly, light was a particle again, or at least something that sometimes behaved like a particle. The wave-particle paradox was reborn. Light is a wave. Huygens, Maxwell tell us so. Light is a particle. Einstein tells us so. How can it be both? How can a wave choose the fastest path? How can a particle know to take it? This is the question I spent my life trying to answer. In 1924, I proposed something that many of my contemporaries found absurd. I said, if light, which we thought of as purely a wave, can behave like a particle, then perhaps particles, which we thought of as purely particles, can also behave like waves. Perhaps everything has a wave nature. Perhaps the electron, the proton, every material thing in the universe has an associated wave. This is what became known as the de Broglie hypothesis, and for it I was awarded the Nobel Prize in Physics in 1929. But that is not the important part. The important part is what it tells us about Fermat's principle. You see, once you accept that particles have waves, and once quantum mechanics developed through the work of Schrödinger, Heisenberg, Born, and others, it became possible to understand Fermat's principle not as a mysterious law that nature obeys, but as a consequence of something deeper. Let me explain how. In quantum mechanics, a particle such as a photon, a particle of light, does not simply travel along one path. In a sense, it travels along all paths simultaneously. This is the heart of quantum mechanics. Richard Feynman, building on ideas that trace their origin in part to my work, developed what he called the path integral formulation of quantum mechanics. In this formulation, you calculate the probability of a particle going from point A to point B by summing up contributions from every possible path the particle could take, every wild, zigzagging, indirect, nonsensical path imaginable. Each path contributes a little wave, a little oscillation, with a phase determined by the time it takes to travel that path. And here is where the magic happens. For most paths, the crazy ones, the long detours, neighboring paths have very different phases. Their waves point in different directions and cancel each other out. But near the path of minimum time, the path that Fermat identified, neighboring paths have nearly the same phase. They add together constructively. They reinforce each other. So the reason light takes the fastest path is not because light is clever. It is not because light evaluates its options and makes a choice. It is because all paths are taken simultaneously, and only near the path of minimum time do the contributions add up constructively rather than cancelling out. The minimum time path is the path that survives the interference of all the others. This is profound. Let me say it again in a different way. Fermat's principle is not a fundamental law. It is an emergent consequence of quantum mechanics. It is what you get when you take the quantum mechanical truth, that all paths are explored, and look at it from far enough away that the wave nature is not directly visible. At the large scale, the quantum mechanical sum over all paths produces the same answer as Fermat's principle. This is what physicists call the classical limit. Classical optics, classical mechanics emerge from quantum mechanics when you look at systems large enough that individual quantum fluctuations average out. This connection between quantum mechanics and classical principles of least action is one of the most beautiful results in all of theoretical physics, and it has a history that runs even deeper than Fermat. Long before Fermat, the ancient Greek mathematician Hero of Alexandria showed that the law of reflection, light bouncing off a mirror, follows from the principle that the path taken is the shortest possible path, not just in time, but in distance for reflection. Fermat generalized this to the principle of least time, and later, in the 18th century, Pierre-Louis Maupertuis, and then more rigorously Leonhard Euler and Joseph-Louis Lagrange, discovered that this principle of minimization applies not just to light, but to all of mechanics. A moving body, a planet in orbit, a pendulum swinging, all of them follow paths that minimize a certain quantity called the action. This is the principle of least action, and it is one of the most general and powerful statements in all of physics. Hamilton reformulated all of classical mechanics in terms of this principle. And when quantum mechanics arrived, Schrödinger, Heisenberg, and eventually Feynman showed that the principle of least action emerges from the quantum mechanical sum over all paths in exactly the same way that Fermat's principle of least time emerges as a special case. So when you ask, why does light take the fastest path, you are really asking a much bigger question. You are asking, why does nature obey extremal principles at all? Why does everything in physics, from the orbit of planets to the path of electrons, seem to be optimizing something? And the answer, as best as we understand it today, is this: nature does not optimize. Nature explores everything, every path, every possibility, all at once. But the paths that survive, the paths that leave a visible trace in the macroscopic world, are the ones where the contributions from neighboring paths reinforce rather than cancel. These are always the paths near extrema, near minima or maxima of the relevant quantity. And so to our macroscopic eyes, it appears as if nature has made a choice, has found the optimal path, when in reality all paths were always present, and most of them simply cancelled into silence. There is something deeply philosophical here that I want to dwell on for a moment, because I think it is important not just for physics, but for how we think about the world. We are accustomed to thinking of the world as made of definite things following definite paths. A ball rolls along the ground. A ray of light travels from here to there. We point to these trajectories and say, this is what happened. This is the path nature chose. But quantum mechanics tells us that this picture is, at a fundamental level, incorrect. What actually happened is that every possible thing happened simultaneously, and what we observe as the definite trajectory is the result of interference, the survivors of a cosmic interference pattern that washes out everything except the statistically dominant path. This has implications that go far beyond optics. In my own work, I argued that the electron orbits in an atom are not arbitrary. They are the orbits for which the electron's wave, the wave I hypothesized, fits exactly around the nucleus like a standing wave on a circular string. Only certain orbits allow the wave to close on itself without destructive interference. These are the allowed energy levels of the atom. Niels Bohr had already discovered these energy levels empirically, but my wave hypothesis gave them a physical interpretation. The electron is not in a specific orbit because of some arbitrary rule. It is in that orbit because only there does its wave survive without cancelling itself. The same principle, constructive interference, selecting the dominant path from a sea of all possibilities, underlies the principle of least time for light, the principle of least action for mechanics, the allowed energy levels of atoms, and much more besides. It is one of the unifying threads of 20th century physics. Now, I want to be careful here because there is a subtlety I have been glossing over. The principle of least time, strictly speaking, is a principle of stationary time, not always minimum time. Mathematically, the path taken by light is one where small changes in the path produce no first-order change in the travel time. This could be a minimum, yes, but it could also be a maximum or a saddle point. In most practical situations, it is a minimum, and Fermat correctly called it a principle of least time. But the rigorous statement is that the path makes the travel time stationary, and this corresponds in the quantum mechanical picture to the region where neighboring paths have the same phase, and this occurs at stationary points of the phase function, not necessarily minimum points. This is the same mathematical structure that appears in Lagrangian mechanics, in the calculus of variations, and ultimately in the path integral formulation of quantum field theory. The same mathematics expressing the same deep truth at every level of physical description. I find it remarkable, and I say this having spent my entire career in theoretical physics, that the question a child might ask, looking at light bending in a glass of water and asking why does it bend that way, leads, when pursued with sufficient seriousness, all the way down to the deepest foundations of quantum mechanics. That is the nature of physics. The surface phenomena are connected by invisible threads to the deepest truths about reality. Pulling on any thread, if you pull hard enough and long enough, will eventually bring you to the bedrock. Let me also say something about what this principle tells us about the nature of nature, about the character of the physical world. The fact that all extremal principles in physics emerge from a common quantum mechanical root suggests that the universe has a kind of internal coherence, a deep structural unity that is not obvious from the surface. Maxwell's equations and Newton's laws look completely different. Light and matter seem to be completely different kinds of things. And yet, at the quantum level, both are governed by the same underlying logic of wave superposition and interference. This unity was one of the great discoveries of the 20th century, and it continues to inspire physicists today who seek an even deeper unification. String theory, loop quantum gravity, and other modern approaches to fundamental physics are in many ways extensions of this same search, the search for the ultimate principle from which all the apparent diversity of physical law emerges as special cases. We do not yet have the answer, but I believe the answer, when it comes, will be expressed in the same language, the language of waves, of phases, of interference, of paths. Before I leave you, I want to return to where we began, because I think it deserves a final reflection. Light takes the fastest path. We have now traced this fact from Fermat's remarkable 17th century insight, through the wave theory of Huygens and Maxwell, through Einstein's photons, through my own hypothesis of matter waves, through Feynman's sum over all paths. At each step, the mystery seemed to deepen and then resolve into something more profound. At each step, what seemed like a brute fact of nature turned out to be a consequence of something deeper and more beautiful. This is, I think, the true lesson, not just the specific answer to why light takes the fastest path, but the method by which physics approaches questions like this one. You take a phenomenon that seems to demand an explanation. You refuse to accept it as a primitive fact. You ask, what deeper principle could produce this as a consequence? And you follow that question wherever it leads, even if it leads you to conclusions as strange as the idea that a particle of light travels every possible path simultaneously. The world is stranger than our intuitions suggest, but it is not arbitrary, it is not capricious. Beneath the apparent complexity and the apparent strangeness, there is always structure, there is always coherence. There is always, if you look long enough and carefully enough, something very close to beauty. That, my friends, is why I became a physicist, and that is why, nearly a century after the formulation of quantum mechanics, it still fills me with something very close to wonder. Thank you.